Hello, it's Dr. Armand again. We're going to bring you an exciting lecture today on acids. Uh, what we're going to talk about today is what is an acid, how do we calculate what's called the pH of an acid, and can we predict the value of K based on what type of acid-base reaction we have. And so, for example, what is an acid? We're going to talk about two types of theories, Arrhenius theory and Bronsted-Lowry theory. When we're referring to the strength of an acid, we're going to be talking about Ka, the acid equilibrium dissociation constant, and pH, a weighted scale, if a solution is acidic, basic, or neutral. And then we're going to talk about how K and how we can predict the sign of K based on the types of acids and bases we have present. So on that note, we'll go ahead and get started today. We're starting a new chapter today on acids, and we'll also talk about bases as well, but mainly this chapter is on acids. And again, everything we learn for acids, the opposite is true for bases. And so just a kind of quick summary with reactions involving strong acids and strong bases. There's always a salt and water produced from a reaction involving a strong acid and a strong base. And the general form of a strong acid is H+. So whenever you see H+ by itself, like in this equation, this is referring to a strong acid. The general form of a strong base, or the reacting species in a strong base, is OH-, I should say that. And the reacting species in a strong acid is H+. The way this differs is for a weak acid, the reacting species is HA. And for a weak base, typically it's like B-. But for strong acid, the reacting species is H+. For a weak acid, the reaction species, or excuse me, for a weak base, a strong base, the reacting species is OH-. And so when you take an acid and put it in water, what happens is the acid gives up its hydrogen to form the hydronium ion, and you form what's called its conjugate base. So one type of theory on acids and bases is called the Arrhenius theory, which is a very simple theory. Arrhenius theory states an acid is a substance with an H in its formula that dissociates in water to yield hydronium ions. So what do we mean by H? Well, this H has to be attached to a highly electronegative. H is attached to an electronegative element. So generally, things like oxygen, sulfur, fluorine, bromine, chlorine, etc. What this does not mean is we're not referring to hydrogens attached to carbons. So hydrogens attached to carbons do not dissociate their hydrogen atoms. And so there are, for Arrhenius acid, for example, if we take HCl and water, we get H3O plus Cl minus. So HCl is an Arrhenius acid. And there are 6, we'll talk about the strength of an acid in a second. So that's the Arrhenius theory, very simple. It says you put something in water, it forms H3O plus, it's an acid. Now a base is a substance that has hydroxide in the formula. That should have, and it dissociates to form the hydroxide ion. So these are usually going to be your group 1, typically your group 1, or usually your group 1 and heavier group 2 hydroxides, because those are also the strong bases. Now ammonia also forms hydroxide in solution, but it doesn't have hydroxide in its formula. So the way this works, if we have sodium hydroxide plus water, we get that. And so hydroxides, soluble hydroxides, are Arrhenius bases. Now the way we categorize acids and bases is based on their strength. And for an acid, it's referred to as a acid dissociation constant. So the acid dissociation constant tells you how much H3O plus is produced per mole of that substance. And if you're referring to a base, it would be the Kb, which is how much hydroxide ions are produced per mole of substance. And so for strong acids, the Ka is very large. We're talking on the order of, 10 to the 5th. Let's just leave it at it's very large. And there are 6 common strong acids. So it's good to remember these because the strong acids are used differently in calculations than weak acids. So 6 common strong acids are HCl, HBr, HI, HNO3, H2SO4, and HClO4. Now weak acids have a Ka less than 1. And the smaller the Ka, the weaker the acid. And the same holds true for bases, for strong bases. There's a high Kb. For weak bases, it's a low Kb. So this is Arrhenius theory. Another type of theory which is more useful is Bronsted-Lowry acid-base theory. So Bronsted-Lowry acid-base theory is based on the movement of the hydrogen ion. And so an acid is defined as a proton donor. So a proton donor, a proton is what the H plus ion is called. If it donates its proton, then it's an acid. So here, HCl and water, we have HCl, we have water. HCl donates its proton to H2O, and you form Cl minus and H3O plus. So HCl is a gas. And all Arrhenius acids are Bronsted-Lowry acids. So if you have an Arrhenius acid, it is a Bronsted-Lowry acid. Now for a base, it's a proton acceptor. So it's going to accept a proton. And so in order for it to accept a proton, the base has to contain a lone pair of electrons to bind to. So this could be a lone pair of electrons on a nitrogen atom, on a single bond oxygen atom, on an anion such as fluoride or hydroxide, but you have to have a lone pair of electrons. If it's a neutral atom, it's going to be a nitrogen atom. So if you have like ammonia, ammonia is a neutral compound, nitrogen has a lone pair of electrons. For oxoanions, it's going to be a single bond oxygen atom that's going to have the lone pair of electrons. Now, Bronsted-Lowry bases are not all Arrhenius bases, but all Arrhenius bases are Bronsted-Lowry bases. So here we have NH3. It has its lone pair of electrons. We put it in water. Water donates, so the lone pair attract a hydrogen, and we form NH4 plus and OH minus. So base accepts a hydrogen, the acid donates, in this case water donates a hydrogen. Notice here that in the bottom example, water is an acid. In the top example, water is a base. And we'll talk about that in a second, or in a little while. Some species can act as a base and an acid. It just depends on what it's stronger as. So one thing I want to talk about here is with Bronsted-Lowry acid-base theory. Not Bronsted, Bronsted. We're going to introduce a term called conjugate acid-base pairs. So a conjugate acid-base pair are species that only differ by one proton. So if two species only differ by one proton, they're an acid-base, conjugate acid-base pairs. So I'll give you a few examples. For example, HF and F minus, those are conjugate acid-base pairs. HCO3 minus and CO3 2 minus are conjugate acid-base pairs. H3O plus, H2O, HS minus, S2 minus. So again, these are all examples of conjugate acid-base pairs. They all differ by one proton in their formulas. And the reason this is important, for example, if we have HF plus NH3 yields F minus plus NH4 plus, and we don't know what's the conjugate acid-base pairs in this. So for example, HF is an acid because it donates a proton. NH3 is a base. And the reason I know NH3 is a base because it's a stronger as a base than HF. HF is a stronger acid than NH3. And then F minus is the conjugate base of HF. And NH4 plus is the conjugate acid. So we were to draw so the ones I've linked are conjugate acid-base pairs. So it's always good when you look at a reaction to identify the conjugate acid-base pairs in the reaction. So the base gives up its, the base accepts a proton, so the base on the product side will form its conjugate acid, and the acid on the reactant side donates its proton, so it's going to form the conjugate base on the product side. Now, one thing you may know is there's something called amphoteric species. And these are species that can behave as an acid or a base. It just depends on what it's stronger as. Besides water, most amphoteric species are anions with at least one hydrogen. That means they have one hydrogen atom that they can donate, or since they're an anion, they can accept another proton. What are some examples? So for example, water is an amphoteric species. It can accept or donate a proton. HS minus, it can accept or donate a proton. HCO3 minus, it can accept or donate a proton. When you accept the proton, the charge increases by +1. When you remove a proton, the charge decreases by -1. H2PO4 minus, what else? HSO3 minus, etc. So there are many examples. These are just a few. And so again, amphoteric species can behave as an acid or a base. It just depends on what it's reacting with to determine whether it's going to be an acid or a base. So for example, if I have, let's see, HNO3 plus HS minus. Here, HS minus is going to behave as a base because it's stronger as a base than it is as an acid. Nitric acid is a very strong acid. So we get NO3 minus plus H2S, for example. So with Bronsted Lowry acid-base theory, you have conjugate acid-base pairs, and you have this thing, these species called amphoteric that can behave as an acid or a base. So here we want to know what's the conjugate base of HCO3. So to make a conjugate base, we got to remove a proton. So to make a conjugate base, we got to remove a proton and decrease the charge by 1. So if we take HCO3 minus, we remove a proton, becomes CO3, and we have to decrease it by 1, so it becomes -2. So that is the conjugate base. Carbonate is the conjugate base of bicarbonate. Now H2CO3 is the conjugate acid. So if it asks what's the conjugate acid, you would add a proton, so this would be conjugate acid. The others are just made up. Now we look at this example. We want to know which of the following is not a conjugate acid-base pair. So what we want to look for, does the formulas differ by more than one proton? So we look at A, does it differ by more than one proton? No. B, does it differ by more than one proton? Yes, it differs by 2 protons. So B is a one that is not a conjugate acid-base pair. Does C differ by more than one proton? No. What about D? Does it differ by more than one proton? No. E, does it differ by more than one proton? That's correct. Yes, because it has a difference of 2. So that is not a conjugate acid-base pair. And does F differ by more than one proton? No. So the correct answers are B and E. Here we want to know what is the conjugate acid of HPO4. So the conjugate acid, to make a conjugate acid, we add a proton and add +1 to the charge. So if we do that, we add a proton, becomes H2PO4, and then we add +1 to the charge, it becomes negative. So H2PO4 minus is the conjugate acid. Now let me ask you this. What would be the conjugate base? So we have to remove a proton and decrease the charge by 1. So the conjugate base is B, the phosphate ions. This is called, just say conjugate base. That looks horrible. Conjugate base. So now we're going to talk more about how do we scale if something is an acid, or if something is, a solution is acidic, or is it basic. So what we want to look at is the equilibrium expression of water. And so here we have the equilibrium expression of the dissociation of water. We have 2 water molecules. We get hydronium ion and OH minus. And so if we write the equilibrium expression, of course, water doesn't show up because it's a pure liquid. And we get Kw equals H3O plus times OH minus concentration. And Kw is 1 times 10 to the negative 14 at 25 degrees Celsius. Notice that Kw is dependent on temperature. You change the temperature, you're going to change the value of Kw. So now if something is a neutral solution, they have to have the same concentration of H3O plus and OH minus. So that's 10 to the negative 7. Because if H3O plus is X and OH minus is X, X squared equals 1 times 10 to the negative 14. You take the square root, you get 1 times 10 to the negative 7. We call that a neutral solution. Next, we have an acidic solution. So what's an acidic solution? Is when the concentration of H3O plus is greater than 10 to the negative 7th and the hydroxide concentration is less than 10 to the negative 7th. We call that acidic solution. Next, we have a basic solution. Basic solution is the opposite of acidic. The hydronium ion concentration is less than 10 to the negative 7th, and hydroxide is greater than 10 to the negative 7th. But as you can imagine, dealing with these tiny numbers, it's hard to kind of scale what an acid or base is. So what do? Well, we use math and we take the negative log of everything. So we take the negative log of Kw equals the negative log of H3O plus the negative log of OH minus. Remember, when you take the negative log of 2 things multiplied, you can rewrite it as adding those 2 quantities, the log of those 2 quantities. We can take the negative log of 10 to the negative 14, and what we get is we get pKw, so we put a P, representing we took the negative log, equals to pH and pOH. So again, pH equals the negative log of hydronium ion concentration, and pOH equals the negative log of hydroxide ion concentration. And pKw equals 14. So pH plus pOH equals 14. So now if we want a neutral solution, notice that the pH has to equal the POH, and that equals 7. So when you have a pH of 7, you have a neutral solution. Now for an acidic solution, the pH is less than 7, or the POH is greater than 7. For a basic solution, the pH is greater than 7, the POH less than 7. Typically we stick with the pH, but just to remember that POH is the opposite of pH. So for acidic solutions, pH is less than 7, POH is greater than 7. For basic solutions, pH is greater than 7, POH is less than 7. Let's do some calculations involving this. Now, all of these calculations are for strong acids and strong bases. So this is for, again, strong acids and strong bases. So if it's a strong acid or a strong base, we can calculate the pH or POH in this way. Remember, a strong acid, HI plus H2O gives us H3O plus I minus. So all of the hydronium ion concentration, I forgot to put a plus sign. Let me put a plus sign there. So all of the hydronium ion concentration comes from the concentration of our strong acid. So if we know the concentration of the hydrogen ion in the strong acid, we know the concentration of hydronium ion. The only time this differs is when you may have sulfuric acid, where the concentration of H plus would be double because there's 2 moles of H for 1 mole of H2SO4. So now we want to calculate the pH of HI, and HI is a strong acid. So the concentration of HI equals the concentration of H3O plus, equals 0.005. So to find the pH equals the negative log of 0.05. And if it's an acid, it should be less than 7. And we get 2.3. It's just common to write pH to the hundredths place. So now we want to calculate the pH of a 0.005 molar of calcium hydroxide. So what we have to note here is that the concentration of calcium hydroxide is half the concentration of OH minus. So OH minus concentration is twice the concentration of calcium hydroxide. And the reason is because there's 2 moles of OH for every 1 mole of calcium hydroxide. So the concentration of hydroxide would be 0.01. Now here, this is hydroxide. Actually, I wrote that backwards. Let me erase this. So it should be 2 times the concentration of calcium hydroxide equals the concentration of hydroxide, which equals 0.01 molar. So we have the concentration of hydroxide. We want to know what's the pH. Remember, pH plus POH equals 14. So if we calculate the POH, we can subtract it from 14 and get the pH. So pH equals 14 minus POH. So POH equals negative log 0.01, which would be 2. Because 10 to the negative 2, the negative log of 10 to the negative 2 is 2. Now to find the pH, it would equal 14 minus 2, which equals 12. And this is correct because the pH of a base should be greater than 7. Now what about if it asked you, okay, instead of finding the pH, what's the hydronium ion concentration for a solution with a pH of 5.55? So what we have to remember here is that pH equals negative log of hydronium ion. So if we wanted to find the concentration of hydronium ion, we just have to rearrange the equation. We get 10 raised to the negative pH. So if we know the pH, we do the anti-log of the negative of that pH, we get the hydronium ion concentration. Oopsie doopsie. Oopsie doopsie. Oopsie doopsie. Again, use the anti-log, and we get about 2.82 times e to the negative 6. And this makes sense. It should be greater than 10 to the negative 7 because the pH is less than 7. Now to the last one, here we want to know what's the hydroxide ion concentration of a solution with a pH of 8.45. So again, what we remember is that pH equals pH plus POH equals 14. So POH equals 14 minus pH. So POH equals 14 minus 8.45. So we get 5.55. Well, that's a convenient coincidence. So the pH, that's not right. Hold on. Oh, it's the POH, my bad. So the POH is 5.55, and then we find the hydroxide ion concentration equals 10 raised to the negative POH, which equals 10 raised to negative 5.55. We get 2.82 times e to the negative 6. Again, it's molar. So again, this is for strong acids and strong bases. This is how you calculate the pH or determine the hydronium or hydroxide ion concentration. Now we're going to focus on weak acids. So with weak acids, we have to understand the meaning of Ka. And for a weak acid, the Ka is less than 1. And so the Ka is less than 1 for weak acids. The greater the Ka, the smaller the Ka, the weaker the acid is. And so for the acid dissociation of a weak acid, notice here we have the double arrow. So we got to write the equilibrium expression. So we get Ka equals the hydronium ion concentration over the times the conjugate base concentration divided by HA. So again, the stronger the acid, the higher the hydronium ion concentration, the larger the Ka. So sometimes we use this kind of, I don't know, you call it oxymoron, I guess, but we're looking for the stronger weak acid. It's not a strong acid, but it's a stronger weak acid. And there are three categories of weak acids. There's those weak acids that have a relatively high Ka, which means it has at least approximately 10% of the solution has dissociated. So for example, chlorous acid, 1 molar solution of chlorous acid is about 10% dissociated. So for this category of acids, you would have to use the quadratic equation, and you can't negate X. So remember that. So these acids with a very high Ka, around the range of 10 to the negative 2, maybe 10 to the negative 3, depending on concentration, you have to do the quadratic equation and solve for the change X. And again, approximately 10 to the negative 2, 10 to the negative 1, 10 to the negative 3. 10 to the negative 3, you'd have to check the 5% rule to see if it's less than 5%. When we get to 10 to the negative 4, 10 to the negative 5 Ka, these are kind of moderate weak acids. And so the dissociation is around approximately 0.31 to 0.3%, such as acetic acid is a moderately weak acid. And so for the second category, moderately weak acids, you can most of the time use the approximation. But if your X is greater than 5% of the initial acid concentration, you may need to do the quadratic equation. And then we have very weak acids with Ka's around 10 to the negative 9, 10 to the negative 10. Very little gets dissociated. And so for the third category, you can probably rest assured that you can use, for most concentrations, you can use the approximation unless it's a very, 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 very dilute solution. So Ka tells us the strength of weak acid. We know how much is going to dissociate. So again, the more hydronium ions dissociate or form from the dissociation, the stronger the weak acid is. And this is just a chart. So at the top of the chart, we have our very strong weak acids, such as chlorous acid, nitrous acid. Then we have, just chlorous acid. Then nitrous acid, hydrofluoric, formic, acetic acid, propanoic. These are the moderate weak acids. And then we have some very weak acids. So let's say we want to calculate the pH for a 0.85 molar acetic acid solution. So what you should note here is that the concentration is roughly 10 to the negative 1. The Ka is 10 to the negative 5. If you take 10 to the negative 1 divided by 10 to the negative 5, you're going to get a factor of 10,000. So you should feel confident that you can use the approximation here. So to calculate the pH of a weak acid solution, we're going to be using you guessed it, the ice equation. So initially, we have 0.85 molar of acid and 0 of product. So you know it's going to go to the right. The change minus X. And for monoprotic acids, those acids with 1 proton, pretty much you're going to be doing the same thing on every problem. Now we have equilibrium. And we get 0.85 minus X x, and x. We're going to have to use the quadratic equation. No, we're not, because the Ka is a lot smaller than the initial concentration. So we can negate this minus x. So then what we get is 1.8 e to the negative 5 equals x squared divided by 0.85. We just work through the math. So we get 1.573 e to the negative 5 equals x squared, and x equals 3.97 e to the negative 3. Remember, x also equals the hydronium ion concentration. So once we know the hydronium ion concentration, pH equals the negative log of 3.97 e to the negative 3, which equals log the second answer 2.4. So the pH of the solution is 2.4. And if you take 3.97 to the negative 3 and divide it by 0.85, you'll see it's less than 5%. It's like 0.46%. So the approximation was justified. And that's how you calculate the pH of a weak acid solution. I mean, unless it's a strong weak acid, 95% of the time you're going to be doing this exact same thing over and over and over and over and over. So here we want to know what's the pH of a 0.07 molar solution of benzoic acid when the Ka is 6.3 times 10 negative. So notice here that the concentration is on the factor of 10 to the negative 2. The Ka is 10 to the negative 5th. 10 negative 2 over 10 negative 5th, like 1,000 times more magnitude in the concentration versus the Ka. So let me write a generalized formula. So we have benzoic acid, call it HBen plus water, yields Bn negative, benzoate plus H3O plus. So we're going to start our ice table. Initially we have 0.07 molar of the benzoic acid, 0 of the products. We do our change, minus x plus x plus x. Now we get our equilibrium concentrations. Excuse me. Equilibrium 0.07 minus x, x, and x. Now again, the concentration is a lot larger, magnitude 1,000, roughly bigger than the Ka, so we can negate the minus x. Doop. And then we get 6.3 e to the negative 5 equals x squared divided by 0.07. Oopsie doopsie. There we go. And then we get x squared equals 4.41 e to the negative 6. X equals 0.0021 equals the hydronium ion concentration. Negative log, second answer. So the pH equals negative log of 0.0021 equals 2.68. That's the pH of the pH of this benzoic acid solution. Again, for weak acids, monoprotic weak acids, any kind of weak acid, I mean, if the Ka is a lot smaller than the concentration, you can be doing this exact same process every time. Now, another thing we can calculate for weak acids is the percent ionization. This is kind of like that 5% rule we've been checking. But percent ionization, let me write it. Where can I write it? Percent ionization means how much acid was ionized equals the hydronium ion concentration. Oopsie doopsie. Oh, snappy. All right. Divided by the initial acid concentration times 100. This is very similar to that 5% rule. And so in this problem, it wants us to calculate the percent ionization for a 4.45 molar solution of hydrofluoric acid. Again, hydrofluoric acid is a weak acid. It gives us the Ka 10 to the negative 4. So look at the concentration factor magnitude of 10 to the negative 1. Ka magnitude 10 to the negative 4. That's like 1,000 times difference in magnitude. So you can use the approximation. So let's set up our ice table. So 0.45. 0, 0. The change minus x plus x plus x. Equilibrium. 0.45 minus x. 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 Now again, small k, lowered concentration. We can rest assured that we're confident we can do the approximation. And now we can solve for x. So we get 6.6 e to the negative 4 equals x squared 0.45. I hope since we've been doing this, you'll see that we're doing kind of the same thing over and over again. We get 2.97 e to the negative 4. And then x equals second square root, second answer, 0.0172. And this also equals the hydronium ion concentration. So now we can calculate the percent ionization. So percent ionization, percent ionization equals 0.0172 divided by 0.45 times 100. It's about 3.82%. So that's the percent ionization of this solution of hydrofluoric acid. That's all you do. Now, if you wanted to calculate the pH, you can do that. Certainly, we just say pH equals negative log 0.0172, which equals 1.76. The answer asks for percent ionization, and that's what it is. So you see it's less than 5%, so we were correct in doing the assumption. So now I want to kind of talk about how do we know the net direction of an acid-base reaction. And this is based on the strength of the acids and the strength of the bases. And so the way you know which way the net direction of the reaction is going to be is based on which side has a stronger acid and stronger base. And on this screen here, you can see that we have a chart. It shows you the stronger acids and stronger bases. And so again, when we have an acid-base reaction, it's always going to go from the strong side to the weak side. So if you look at the acids on both sides, whichever one is stronger is going to shift to the weaker. So here, in the first equation, we have H2S, which is an acid. And you can do the same thing for bases. You only have to do it for one of them. And we have NH4+. And then you check to see which one is a stronger acid. So H2S is right here. Look at the diagram. NH4+ is right here. So H2S is a stronger acid than NH4+. Could be multiple number of reasons. One reason could be that sulfur is more polarizable than nitrogen, so it's easier for that hydrogen to remove. Regardless, the net reaction is going to shift to products. So that means the KC is going to be greater than 1 because it shifts to the right. Next, we have HNO3, which is an acid, and H3O+. So we come here, look on the diagram, HNO3, located right here. H3O+ is below it, so H3O+ is the weaker acid. So it's going to shift to the right, or it's going to net direction is going to be to the right. And so Kc is greater than 1. Anytime the net direction is to the right, Kc is greater than 1. To the left, Kc is less than 1. Look at the third equation. We have HF, which is the acid, and H3O+. So here we look, okay, H3O+, we've already looked at that earlier. It's right here. HF is below H3O+. So it's going to shift or net direction to the reactants. So Kc is less than 1. And you may say, well, why is H3O+ stronger than HF? One of the reasons could be that F is so electronegative that it's holding on to that proton very tightly and it's very hard for it to be removed. Whereas H3O plus, it's in the cationic form, it can remove its H a little bit, easier than that H that's attracted to that F, very strong, very tightly held. And so that's how we can identify what the relative K would be for an acid-base reaction, remembering that it always goes from the strong side to the weak side. Just to give you a little bit of prelude to bases, so NH3 is a stronger base than HS minus. And the reason that it is the opposite of the acid. So since N is less polarizable than S, it makes it a stronger base. So now let's look at this reaction and determine whether we can identify what Kc would be for this equation, this reaction. So we look here, the acids are H2PO4 minus because it donates a proton, and obviously F minus can't be an acid, and we get HF. And the reason we know that the acid on the product side is HF and not HPO4 2 minus is because the acid on the reactant side is H2PO4 minus. It donates a proton. So since it donates a proton, it's going to form its conjugate base. So this is the conjugate base of dihydrogen phosphide. And then F minus accepts a proton, and HF is the conjugate acid. So we look here, where's HF? HF is right here. Where is H2PO4 minus? Down here. And since HF is a greater, stronger acid than H2PO4 minus, it's going to shift to the, it's going to, net reaction is going to be to the left, so Kc will be less than 1. Now we get to this one, and if you got your phone, you've been Facebooking, now it's time to pay attention because this is very important. We're dealing with organic acids and bases. So pay attention here, this is very important because here there's no chart. You have to use some guidelines to help you understand which one is the stronger acid. I'm going to take a break, just a quick break. All right. So here we have, let's see, this is 1, 2, 3, 4, 2-chloro-butonic acid plus pyridine gives us the pyridinium ion plus 2-chlorobutanate. And we want to determine what the Kc, whether the Kc would be greater than 1 or less than 1. So pay attention here, this is very important. So first off, let's identify the acids. Well, obviously the acid on the reactant side is the 2-chloro-butanoic acid, and on the product side it's the pyridinium ion. So now we've narrowed down the acids, and both of these are organic acids. One's a cationic form, one is neutral form. So we got to determine which one is the stronger acid. So let's investigate the atom that's attached to the acidic hydrogen. So we look here, it's OH. Here it's NH. Okay? So since O, oxygen, and nitrogen are on the same period on the periodic table, the one that's more electronegative will tell you which one is the stronger acid. So again, when you're comparing the atom that's directly attached to the acidic proton, and they're both on the same period of the periodic table, you look at which one has the greater electronegativity. Let me repeat that again. Since we're comparing the atom that's directly attached to the acidic proton on two different acids, and since those atoms are on the same period of the periodic table, we look at which one has a greater electronegativity, and that's going to tell us the one that's a stronger acid. We just repeat it one more time. So since we're comparing two acids where the element that's attached to the acidic proton are both on the same period, we look at which one has the greater electronegativity. It's going to tell us the one that's the stronger acid. And so oxygen is more electronegative than nitrogen. So this would be the stronger acid. So we'll call it SA. And this would be the weaker acid. And so it's going net reaction to the right. Kc is going to be greater than 1. In addition to what we just talked about, the electronegative element, if, for example, they were both oxygen, then you would see which one had resonance. So, for example, this one has resonance. So the one with more resonance, when both atoms attached to the acidic proton are the same, you go to resonance. Look at which one has more resonance. That's going to be the stronger acid. And in the next lecture, we'll actually be talking more about these rules. But main thing what I want you to grasp here is that you look at the element attached to the acidic proton. Since they're both on the same period, you see which one is more electronegative. That's the one that's going to make the stronger acid. So that concludes today's lecture on what is an acid, the different theories of acids, how do we calculate the pH of a solution to determine if something is acidic, basic, or neutral, and also to predict the Kc based on the acid-base equation. So on that note, until next time, Dr. Armand signing off.